What is up, everybody? So we are moving on to our second transformation, which is called translation. Okay. So before we do that, let's just quickly go over a little review of reflection. Okay. So remember, when we're reflecting over the x-axis or the y-axis or a horizontal or a vertical line, usually it's best just to count the difference and just flip your figure over that line of reflection and making sure that each point is equidistant from the line of reflection, right? So even though there's a rule for the x-axis and the y-axis, it's usually just really quick to count the spots on the vertical and the horizontal lines. Now, if your line is y equals x or y equals negative x, so those two diagonal lines we covered, then I highly recommend that you follow the rule at the last two lines right here. Okay, so just remember, right, that when you're doing a reflection, there should be symmetry, meaning both sides have the exact same shape and size, and if you were to fold a piece of paper down that line of reflection, then your two figures should lay over the top of each other. Okay. Now we're moving on to translation. And translation, to be honest, usually requires the least amount of work and can be done the fastest. So translation is the transforming or moving of a figure along the path of a vector. Now I'll talk about what a vector here is in a second. Now you think with reflection, you're picking something up and you are flipping it over, right? So that it looks the same as far as shape, but the direction it's pointing or facing, depending on how you want to look at it, is different. With translation, the orientation of our figure never changes. It doesn't flip, it doesn't rotate. Just imagine if you picked something up, didn't twist it or turn it, and put it back down in a different location. That is a translation. Okay? Or think of it as a shifting or a gliding from one spot to another. Right? Again, you're not turning it, you're not rotating it, and you're not flipping it at all. So a vector is a ray that represents movement. So for us, ray, you think of it starts at one point and it goes to another. I know ray in Unit 1, we talked about how it starts in one point and goes on forever and ever in one direction. In this case, a vector has a start and a stop point. But it's going to look like a ray when we draw it in. Now, you don't have to draw the rays in or the vectors, but when you do, it kind of creates this three-dimensional figure, and it's a way to check your answer just by the eye test to see if you think you did it right or not. So, translation is represented in two different ways. One is called coordinate notation, and one is called vector notation. They both are representing the same thing. One is just a shorter to write, while the other one gives you a really good idea of what should be happening. So with coordinate notation, it looks very similar to our rules, right? So if we look at all of our rules up here, you have your original coordinates, right? Like those are our original coordinates. So here, these represent our original coordinates. And then when you translate, you are going to be adding or subtracting something to every x and every y. Now, it's not the same thing to x and y. However, the same thing must be done to all the x's, and the same thing must be done to all the y's. So like I could put a 5, x plus 5, and y plus 3. That would mean I'd add 5 to every x, and I'd add 3 to every y. Okay, so we'll get to an example here in a second. Now, vector notation is much shorter, and it just looks like this. It has those two arrow brackets. So the A right here is referring to this A here, and this B is referring to this B here. They mean the exact same thing. It's just one is a much shorter way to write it. So let's look at triangle ABC. So triangle ABC is A is at 1, 2, B is at 3, 5, and C is at 5, 3. Now we want to translate that using this rule, xy, x minus 3, y minus 2, or notice again, like I said, we have it in vector notation. So all this means is that I'm going to subtract 3 from every x value, and I'm going to subtract y from every, I'm going to subtract 2 from every y value. That's all translation is, nothing else. All right, so let's start with point A. So when I look at point A, I'm going to go, now if I subtract 3, now subtracting 3 from x, that is or adding 3, that is a horizontal movement. So my x is moving this way, and my y is moving this way. Now you can do this in 2 different ways. If you only have the coordinates, you can write them out on the left-hand side, or just write them out, apply the math, and then graph. If you have a graphed figure for you already, it might just be easiest to count it on the graph. So here's what I mean. I'm subtracting 3 from my x, so that means that's a left movement 3 points, because I'm going left because I'm subtracting. And then I'm subtracting 2 from my y. Well, if I'm subtracting from y, that is a vertical movement going down. If I was adding 2, I would be moving up. So that would be down 2. So my new point for A prime is going to be right there. Now I could have just done subtracting 3, so 1 minus 3 is negative 2. Subtracting 2 from 2 is 0. Notice you end up at the exact same spot, negative 2, 0. So that is the location of our A prime. And you're going to do that for every single point. So 1, 2, 3, 1, 2. So B prime's right here. Let's just check our math really quick. 3 minus 3 is 0. 5 minus 2 is 3. 0, 3, it works out. 1, 2, 3, 1, 2. Kind of overlaps our first point a little bit. So there's C prime. Again, subtracting 3 gives us 2. Subtracting 2 gives us 1. At 2, 1, perfect. Let's go ahead and connect those dots. Okay. So we now just translated triangle ABC by a vector of negative 3, negative 2, or vector movement of negative 3, negative 2. Okay? So now here's what I said you can kind of draw in the vectors to check your answer. So if I were to draw some dotted lines right here, it creates this 3-dimensional figure, right? And all of those lines have the same slope, so they're all parallel. And if I was to take a ruler to this, all of those lines would also be the exact same length. Those vectors would be the same length. Okay? So if you were to do yours and all of a sudden for some reason you notice that one vector was way longer than the other, that's a good eye test to see that you probably made a mistake somewhere. Okay? So again, guys, it's just applying the vector or the translation rule to whatever figure you have, and you just shift it. So notice that A, B, and C, they're all in the same orientation. A is on the left, B is on the top, C is on the right, whether it's the original pre-image or the image. Compare that to when we were doing reflection. Sometimes the positions of them would drastically change, right? When you're looking at a reflection, your left is your right's your left. When we're doing translation, that's not the case. Let's try it on a little bit bigger scale here. So I went ahead and graphed out a quadrilateral for us. And we're going to translate this by now +4 and +3, right? So I'm going to do this without adding to any of my points up here. I'm just going to count the points. Now, since I'm adding 4 to x, that's a horizontal movement to the right. And since I'm adding 3 to y, that's a vertical movement up. So my new figure should be somewhere kind of in this area, right? So again, every single one of these points moves to the right 4 and up 3. 1, 2, 3, 4. 1, 2, 3. So here is our H prime. 1, 2, 3, 4. 1, 2, 3. Here is my G prime. 1, 2, 3, 4. 1, 2, 3. Here is my E prime. 1, 2, 3, 4, 1, 2, 3. And here is my f prime. Let's go ahead and connect those up. Oops, forgot to make my line not dotted anymore. And again, if you want to, you can make that, draw that those lines in just to check your drawing, right? And it should make a nice little three-dimensional figure, depending on how you want to look at it. The purple could be in the front, the pink could be in the front. But if you were to take a ruler to this, and if you were doing it on graph paper, then all of those vectors should be the exact same length, because you moved every point the exact same amount. All right? And that's translation, guys. Like, there's not that much more to it. Like I told you, this was probably the easiest transformation of the bunch. So the first part of your homework, you're going to just be translating just like we did, right? Quick reminder, the vector notation of this would be 4, 3. Okay, so if you ever see this, it's talking about a vector notation translation, but it means the exact same thing as that. All right? So now the second part of your homework is you're going to be given a translation, and you have to figure out, like they're going to give you the graph of a translation. So just like in the last homework where they showed you the reflection, you had to find the line of reflection. In this case, I'm going to give you a couple translations happening, and you got to tell me what the rule was or what the movement was. Okay? So let's start off with these two here. So now you could look at the points, right, and try to count it out, or excuse me, not count it out, but like try to look at the pre-image coordinate and the image coordinate and do the math. But I usually advise that you just look at the movement and count that in. So first things first, we have to be able to know which one's my pre-image, which one's my image. And the way that we know that is we have our prime notation, right? Because we have our apostrophe. So that means this is after the translation, that point down at the bottom. So the first thing let's look at is let's look at the horizontal movement. So let's just go from A to A, right? So does it move anywhere left or right to get from A to A down here? The answer is no. So if there's no movement, we just put X and we don't add or subtract anything to it. All right? Again, if there's no movement horizontally or vertically, depending on which one we're looking at, if we're looking at X right now, there's no X movement from A to A prime. We're not moving left or right. We still have to put the X. We just don't add or subtract anything to it. So what that means is the X is unchanged. Then let's look at our vertical movement when we're going down 1, 2, 3, 4. So that means our Y value is decreasing or subtracting by 4. Just to make sure, 1, 2, 3, 4. 1, 2, 3, 4. Cool, everything's good. So to get from A to A prime, we don't go left or right at all, and we just go down 4. Now, what would be the translation to get from prime to what we call double prime, double apostrophe? Okay, so let's look for that rule now. Well, to get from A prime to A double prime, I have to go left 1, 2, 3, 4, 5 units. So since I'm going to the left, that is decreasing in X value, so I subtract 5. Then to get to A double prime, 1, 2, 3, 4, 5. 1, 2, 3, I go up 3, so my vertical movement is 3, so that is Y plus 3. So my rule to get from prime to double prime using translation is X minus 5, Y plus 3. And then, guys, if we are doing this in vector notation, that would just be 0, negative 4, and this one on the left would be negative 5, 3. And that's all I got for you in translation. Have a good day.